Hi and welcome to our second rendering lecture. My name is Adam Zellerek and I will be talking about light. So first, let's make an overview of the lecture. We will start by talking about some intuitive properties of light, then we will make some simplifications because we don't need to compute all the physics. Later we will explain the math behind our computations, introduce some physics, some physical properties like irradiance and radiance, and finally we will see how to apply what we learned to compute direct light, or in other words, soft shadows. The first property is that light travels in straight lines. This is how we can do ray tracing, and this is also how we can use lasers to tease cats. Next, the angle theta plays a role. When the light shines on the surface by a right angle, 1 unit of light reaches 1 unit of the surface. However, when we tilt the surface or when we tilt the light, 1 unit arrives on a larger surface area. And so the density of the photons becomes lower, and so the surface is lit less strong. And the percentage of light is precisely the cosinus of the angle between the normal and the incident light direction, which can be calculated using simple trigonometry. Right here, the cosinus is the adjacent leg divided by the hypotenuse. If we want to compute how much light arrives at a unit length, we can set c to 1 and we get cosinus of theta. Done. Obviously, you will compute that in practice by taking the dot product between the normal and the light direction. Next, intensity. Obviously, that plays a role. A brighter light gives a brighter surface. This relation is linear, which also shouldn't be surprising. The size of the light source. Now that relation is a bit trickier. It's not linear. We will see the math later. For now, just imagine you are standing 1 meter in front of a flat rectangular light source that has the same brightness everywhere. You would look brighter if you increase the size from 10 centimeters to 1 meter. But the change would be minimal if you increase the size from 1 kilometer to 100. This is because for far away points, the angle theta is very low and also the distance is very large, which is leading us to the next point. Distance to the light source. You probably know from previous courses that a point light attenuates with 1 over distance squared. This is simple to explain. Imagine light to be the skin of a balloon growing around the source. The balloon grows because light travels away from the source. The number of light particles doesn't increase when the balloon grows, so the density is inversely proportional to the surface area of the balloon, and the surface area of a sphere grows by the square of the radius. Good. Okay, but how should we put all that into a coherent framework? We have to focus on what's important, the brightness of a certain point on my surface. How bright something is doesn't directly tell you how brightly it illuminates something. Usually, I would show you this in the lecture room by bringing a large lamp and telling you to form a shield by your hands with a small hole. When you get closer to the lamp, the brightness that you see through this hole doesn't change. It also doesn't change when I tilt the lamp. However, when you take a surface and you bring it closer to the lamp, it does become brighter. It also becomes brighter when the angle is closer to 90 degrees. So if you tilt the surface, it will appear darker. And this is the point where I usually would allow for questions. However, we don't have a lecture, we have a YouTube video, so I will repeat what we just learned. Light travels in straight lines, the cosinus rule is important, the distance is important, the intensity and the size is important. Next, we will show some less intuitive effects. For instance, fluorescence. Those are materials that change their wavelength. For instance, they turn UV radiation into visible light. A good example of this are stripes on ambulances that appear brighter than they should. The next thing is polarized light. There are different types of polarization, linear and circular, and the circular polarization can be clockwise or anti-clockwise, and linear polarization can have different angles. I don't know how this photo was made exactly, but the laptop screen emits polarized light, the glasses are a polarization filter, and there is another filter on the camera. This is another example. A laptop screen was used as a polarized light source. Then a polyvinyl chloride ruler was photographed using an analyzing polarizer in front of the camera lens. The color patterns are due to interference caused by phase retardation of the light going through the plastic. Internal stresses were frozen when the plastic cooled, creating a stress tensor field that resulted in a varying B refringence, which is seen by a spectral color pattern. In here, we see quantum entanglement. The photo shows the interference pattern produced by a green 532 nanometer laser beam passing around a wire of a thickness of 0.254 millimeters at a distance of about 4.5 meters from the wall, acting as a screen. The interference pattern is created by individual photons interfering with themselves. It occurs even when the intensity of the light is so small that only one photon leaves the laser at a time. You guessed probably right, those are the simplifications, things that we will not compute. We use ray optics, also called geometrical optics. So we don't account for phenomena like diffraction or interference. Rendering an optical disc is pretty hard. We also have no energy transfer between frequencies, so no fluorescence. In this course, we will disregard the spectrum and just compute RGB, though production renderers often simulate spectrum. And finally, we will ignore polarization. The next topic is math. We will learn how to compute the amount of light that reaches a certain point on a certain surface. Okay. We have to sum up of the light. Yes, those are integrals. We have to sum up over all of the incoming directions. So we have to sum up over the hemisphere. For now, we will ignore light coming from inside the materials, like for instance glass or participating media. Here you see the integral that is used to compute the receiving light on the surface. We have the integral, which integrates over the whole hemisphere. It looks into all directions, which is in a way encoded into the solid angle. We have the cosinus rule here, and we sample the light using ray tracing from different directions. This is not useful for rendering yet, but we will come to that. Compare this to a traditional 1D integral from basic calculus. We have the differential, which in the traditional case is dx, in our case it's d omega, and we have the domain. In 1D this stretches from A to B, while in our integral this is the hemisphere, denoted here by the large omega. And as we said before, usually the cosinus rule is computed using the dot product. So what's going with that object size, distance, etc.? The illumination power is determined by the solid angle subtended by the light source, simply how big something looks. And the solid angle, this is this differential. Let's start with 2D. Say this is our light source and this is the angle. You see, when the light source comes closer, the angle becomes bigger. So this means that our point is illuminated in a brighter way. The angle, alpha in radians, is the length on the unit circle. The full circle is 2 pi. So the amount of light that reaches our point directly depends on this angle. When we go to 3D, we have the solid angle. And the rest works pretty much the same. But the unit is now steradians, and the full solid angle is 4 pi, which is the surface of a unit sphere. Now we want to look at the relationship between a surface patch, again this is a differential right now, and the solid angle, which is the differential on the unit sphere. Those two differentials represent the same thing. We have here a small surface patch, while here we have projected this surface patch onto the unit sphere. The solid angle in here also encodes the direction, while the surface patch also encodes the position in the world. And we already said that those two are both differentials from an integral. The relationship between the surface patch and the solid angle can be described using this formula. Don't confuse this cosinus with the cosinus of the receiving surface, which would be here. This cosinus is measured over here. This relationship holds for infinitesimally small surface patches dA and the corresponding solid angle d omega. For larger surfaces, we would have to integrate over the whole surface and use many small tiny patches dA. Do you see where we are going? Towards change of variables, from dA to d omega. We can integrate over the surface of S, so over the light source, instead of integrating over the unit hemisphere. We have seen this integral before, but now we want to integrate over the surface of a light source and not over the hemisphere. These are the changes that we have to apply. We've seen the relationship between the solid angle and the surface patch before, and we can just exchange them. If we do this, we also have to change this one. Instead of measuring the light which is coming in from a certain direction, we measure the light that is emitted from the surface in this patch. Okay, and since it could be hard to imagine how that works in practice, here I've expanded all the variables. We employ numerical integration. That means that we have to evaluate the integral at certain points. These points are y. Here, 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 and here. They are used together with the point x on the current surface to compute the whole thing. This thing is the radius squared. Here we have the cosinus at the emitting surface. Here we have the local cosinus, and this means that we are integrating over the whole surface. We have seen the light integral. We have seen how to compute the amount of light that reaches a certain point. Next, we will come to physics. This is an overview. We will first briefly cover the electromagnetic spectrum, then we will go a bit into radiometry and photometry, that is units and how stuff is perceived by human eyes. Then we will go a bit more into radiance, and finally we will look at stuff that is important for rendering. First, the electromagnetic spectrum. Gamma rays, X-rays, visible light, infrared, microwave, radio waves are all the same physical thing, but with different frequencies. Visible light is just a very small band of it. It divides into blue, green, and red light. When we do rendering, we sample this visible light at 3 different points, because we only render with RGB. However, production renderers often use more complicated material models, and they would sample the light at many different positions. Then makes it possible to simulate reflection functions and, for instance, even fluorescent materials more precisely. This is a work by Wenzel Jakob and Johannes Hanecker, which instead of using this sample that we saw before, they use functions. These functions are an efficient way to store a description of the electromagnetic spectrum. They can be used for emitters, for the surface materials, and they can be combined in an efficient way. Look at the paper if you want to see more details. Next, we will cover some radiometry. That means units and naming. It might be a bit boring, but it's also important. I will use an analogy of rain or water droplets. This analogy might be a bit weird, but it will work out great. And I hope that it will make things bit easier to understand. First, radiant energy. So this means how much rain is in the air in total. The flux, or the power, is how much rain or water is there in total in a given time. Radiant intensity, how much water falls into a certain direction. You see there the radiance or the solid angle. Then irradiance, how much water falls on a given area. Then radiant excitance, how much water is coming out of the cloud per square meter. Then radiosity, imagine the rain is flying up into the clouds, being reflected by the clouds, and the clouds add some rain. Then radiance, it is the same, but per direction and per area. And finally, radiometric quantity per wavelength. Next, we will see a bit about photometry. This is measurement of perceived brightness. The human eye is most sensitive to green light, then to red light, and least sensitive to blue light. This is why yellow light, which is a mixture of red and green light, is perceived brighter than blue light. In rendering, sometimes we have to account for that. Radiance is a physical unit, while luminance is a photometric unit. There are also units and names. This table gives you an overview. We will not go through all of these, but look at Talbot. It's an interestingly named unit. Okay, let's go back to something serious that is actually important. Radiance is the fundamental quantity that simultaneously explains both the light source size and receiver orientation. So this is what we will be talking about. Let's consider this beam of light. It has a cross-section of dA. This is a differential, so the cross-section is infinitesimally small. The direction is also not a single direction, but a differential direction. So the range of directions is infinitesimally small. Let's look at the formula. We have the differential flux per unit projected area, again differential, and solid angle. This projected area means that we take the angle theta into account, and we have the units which we have seen before. Now, using this, we can count energy packets. Each ray carries the differential flux, so it is an infinitesimally small amount of energy. And sorry for the different notation, the picture and formulas were taken from different sources. We have a small solid angle and a small surface patch. So we are counting the rays. When we make the solid angle smaller, we have fewer rays, so this means less energy. In the same way, when we make the area smaller, we again have fewer rays, and this again means less energy. So this means that radiance is a density over both space and angle. Sensors are sensitive to radiance. With sensor, I mean, for instance, the human eye or a camera or our virtual sensor in a rendering system. It's what you assign to pixels. So when you see a rendered picture, the pixels are the measurement of the rendering simulation. This is the fundamental quantity in image synthesis. Intensity does not attenuate with distance. This is what we learned. Light travels in straight lines. All relevant quantities, irradiance, etc., can be derived from radiance. When light leaves a certain surface patch into a certain direction, this is radiance. Light arriving at another surface patch is radiance as well. We just flipped the direction. Radiance exists in empty space, away from surfaces. So you can take a 5D function, 3 dimensions for the position and 2 dimensions for the direction, and this function can completely describe how light behaves in this point. Sometimes this is called the planoptic function. Let's now look at the flux that is sent from this surface patch towards this one. We have the formula here. It is very similar to what we have seen before for the integral of the incoming light. We have the solid angle in here, we have the incoming cosinus here, and we have an additional differential here. This is because we have now a surface patch and not a single point. and this is the flux. So we can compute this using the position 1 as a reference point or the position 2. If we use the position 2, this part changes. We have a 2 in here and a 2 in here, and the direction is inversed. So when we compute it from position 2, we have this. From position 1, we have this, which we saw just now. And you can see that all these terms on the right side are the same. And this results that the flux coming into position 1 is equal to the flux that is leaving position 2. Oh, cool. This means that the amount of flux is constant along straight lines. Basically what we said before, but here we have it in math. We will now cover some more physics that we will need later for rendering. Irradiance, it is the incoming light we've basically seen before, but we will have a brief repetition. Then we will take a look at materials, but just very briefly, and we will see what the white furnace test is. It's a test for energy conservation, and it is also very important. So this is what we saw before. The integral of the hemisphere, we test all directions, we take the cosine into consideration and the solid angle. This is an integral of the incoming light. It gives us the amount of light that is received by a certain surface point. However, it doesn't tell us how much light is directed towards the camera. The material in point X is important for that. If the material is completely black, it will absorb all of the light and nothing will go to the camera. The material is modeled by the BRDF. The BRDF means bidirectional reflectance distribution function. It tells us how much light is reflected from a given direction into another given direction at a given position and in which wavelengths. So the wavelengths basically means the color. You probably implemented some simple BRDFs in one of the previous courses. And we will cover that in more detail in later lectures. The white furnace test. A material cannot create light, otherwise it would be a light source. This is pretty basic, but when you are implementing something, you can make errors. So this white furnace test can be used as a unit test. Basically, it works as follows. We set this term, the amount of incoming light, to 1, and then check the outgoing term. It should be below 1. If it's greater than 1, we have an emitter, and we don't want that. Okay, cat, let's set this to 1. The incoming light is 1 everywhere. Let's further assume a white diffuse material, so all of the light is reflected. And now we want to check that this integral gives us something smaller or equal than 1. We can guess that it will be 1, because we have a white material and white incoming light. So let's do it. Okay, cat, how can I integrate that half sphere? Well, if you have a problem with integration, you can throw change of variables at it. Let's do that. I will not go into details of how this works. You can look it up on the internet somewhere. It is basically the change of variables that is needed to integrate over a full sphere. And then we divide by 2, so we have the half sphere. This is the result of the change of variables. You have the cosinus, which we saw before in here, and the sinus and all the rest is from the change of variables. What we do is going here the full circle, and here we are going the half circle. So this is responsible for turning that way, and this is responsible for turning this way. We can compute the result using Wolfram alpha, and it says pi. And, well, pi is greater than 1. Didn't we say that it should be smaller than 1? Oops. this white furnace test failed. Okay, and the resolution is that the BRDF of a white material is 1 over pi. In general, diffuse materials is rho over pi, where rho is the color. Okay, and this concludes our section about physics. We covered quantities and units, we covered materials, and finally the white furnace test. Next, we want to see how to apply what we learned. Soft shadows, or direct lighting. This is what we already saw before in the math chapter. We have two versions of this integral. One of them is over the hemisphere and the other one is over a light source. In the physics chapter, we added the material. So now we want to combine those two. We have made the change of variables for the light source. We have the receiving cosinus. We have the light intensity on the light source now, and we have the material. But this is not all. Something is missing. Do you know what? The visibility term. It is computed using ray tracing. If we are on this point, our rays towards the light source are blocked, and then it becomes 0. If we are on this point, this ray is not blocked. However, if we take a point in the very far corner, it is blocked. And so this equation you can use for rendering. And here you see the same equation but expanded. Similar as before, we have the dot product for the cosinus, we have the distance, we have another dot product for the other cosinus, and the rest of the terms stay the same. Until now, those are all just integrals. We don't know how to compute them. We can guess that it will be a numerical method, but we don't know yet which one. And this is the next page, but it will have a slightly different notation. The material will be now a diffuse material of color rho over pi, which is the BRDF, and the emitting light will be just called E of y. And this is it. Here we have moved this rho over pi out of the integral because it is constant. And the integral we want to estimate with something which is called Monte Carlo. For each visible point, that is, every point that is visible by the camera, we first make a raycast from the camera into the scene, and then we have the visible points. We generate n random points on the light source, store the probability, which depends on the surface area of the light source. We start with 0. Then we iterate over those points. We cast shadow rays. This is the visibility function over here. If it is visible, we increase the estimate by the intensity of the light, the receiving theta, the solid angle, and we divide by the probability. And finally, we divide all this by the number of samples and we multiply it with the color. This is an intuitive picture. P is one of the visible points. So it was cast from the camera and it landed here. If we now sample the light source, we can estimate the percentage of light that is coming through. Obviously, I've skipped ahead of our lecture. We will see much more of Monte Carlo in the next lesson. However, you can try to implement something simple like this just as an experiment. You can pretty much translate the pseudocode that I've shown just before into actual C++. Next time, as already said, we will hear much more about Monte Carlo. We will learn how to compute pi, and we will learn about uniform sampling, importance sampling, and how to apply this to compute ambient occlusion. So that was direct lighting. We have seen the change of variables and we have seen how to apply Monte Carlo, but just a sneak peek. As said, the next lecture will cover Monte Carlo method more in depth. And the reading links you can get from the slide set that is posted on our course website. I will link the course website in the description. That was it. Thank you.